I'd like to clarify something that I realized was not clear at all. That's a good thing of having multiple lectures, so you can always come back and try to solve stuff. So it's important, and I sort of started saying things like that, but so it's important that, so we have gravity on one side, and we have the field theory on the other. And it's important, I think this of course we know, but it's important to restate exactly what is going on. So here we have a space radius 5 times 5. And again, so the sphere I think everybody more or less knows. So it's very symmetric object, and similarly it's ADS. So I try to convince you that there's some hypersurface that is kind of like a sphere, but with some funny signature, but other than that, it's very symmetric. So, in fact, everything is characterized by one scale, okay, which was this L. Okay. So now, for spaces like this, if I want to be in a good gravity description, so everywhere I need GS very small, right? Just to be sure. Here, because in any case, I don't want to have to deal with string splitting and joining, all these kind of processes I want to completely suppress. You need a picture, so really this is very important. So then the only real scale that matters here is this. And if I want to, for example, to compute the Ricci scalar of something like a sphere, what would be the dependence? Right, so there's a number. So actually, we can be a little bit more precise. So unfortunately, the Ricci scalar here is 0 because it cancels here and here. But let's just take the S5 part. Okay, so it would be some number. So it is positive, of course, in some convention. It's some number, and then the only scale I have is this L squared. So if I want very small curvature, so that my gravity is well defined. In the classical limit, I need this L squared to be large. So in this picture, I want L to be large. Okay, and L. So I think we wrote it. This. Okay, so this I of course this did not come from. So maybe I look at I write it for you in its rightful. But I should have written GS, but I'm using this amount. So this would be a picture, this would be a regime. So this number has to be large, the appropriate units. So in this picture I have the Yang-Mills coupling, and then the only other coupling I had was the Hopf coupling, which most people call it lambda, and it's G Yang-Mills squared N. Now, Yang-Mills is already small. If I want to have some perturbative, I show you some diagrams, and I show you that for the planar computation, I will have to so many diagrams in which the effective coupling was lambda. So of course, if I want that to be a sensible description of the theory, this number has to be small. So field theory would be a very good tool to describe the physics that I'm interested in this regime of parameters, whereas gravity is going to be a good description in this regime of parameters. So they are, of course, non-overlapping regime. That's a good thing and a bad thing, but at least it's useful, and this is sometimes people call strong-weak duality. Again, these are no words that I necessarily adhere to, but these are words that you might hear. And then people say, okay, and what this means is essentially that this description, this description is weakly coupled, lambda large. When this one is lambda large, here would be strongly coupled. So there are some computations in field theory that could involve large coupling. Like if you are interested in understanding some dynamic in QCD, for example. that would be inherently the strong dynamics. So that is notoriously difficult to do with field theory, but now with this equivalence, we can say, okay, maybe I can find a gravity computation that mimics the dynamics that I'm trying to describe using field theory. But the key thing is that I wanted to highlight is that we have these different regimes where the theories are applicable. So what I want to do today, or in the next hour or so, is to continue with the introduction. So I told you that two theories are equivalent. Now I need to give you some recipe for how to work with that. So let's build that. Okay, so actually let me I'm going to write my plan here again if I get to it or not. Let's see. So one thing I want to show you is how to compute correlators. So this is still introduction. Then I want a formula for correlators, and then I want to talk about, this is a simple Wilson loop, but I want to introduce that one if I can today. So that's the plan for now. Okay, so let's consider a scalar in ADS5. So now, why would I do that? I have to consider gravity or ball fields in ADS5 process 5. I don't want to spend a lot of time, but I can convince you that the dynamic on S5 for a lot of questions is not really the most interesting part. Here I can do some expansion in spherical harmonics. And what I need to learn is how to deal with fields in ADS5. I will come back to make connection with this full picture, but grant me that this is really a key ingredient in what we are going to do. Okay? So let's consider some scalar field. So this is some constant, and then so the metric that I want to consider in ADS is 1 L squared over Z squared. This is squared plus W mu. So this one I don't think I wrote in the morning, so you might be a little bit confused, but this is also ADS5. So the difference between, so in the morning I used some coordinate R, and I think if I use some transformation like this, I'll get this matrix. Some metrics are more convenient than others. This is going to be useful for us. Okay, so what I need to do is to study the dynamic of this field and hopefully connect with field theory. That's what this part introduction, and then how to get correlated. So the dynamic of this field, the equation of motion for this field is Klein-Gordon. So it's essentially, so let me write it like this. So I have to solve this equation. Okay. Let's write the Laplacian. It's going to be something like this. A second. Okay, so I don't have a lot of time, so I'm going to skip some steps, but I will explain what I'm doing. So can everybody write if I give you a metric, can everybody write the Laplacian for the given metric? Sorry? You're not sure?
Yes.
Yes, okay. Good, so I mean, I'm happy to explain anything. So if you want me, I can do that, but I think that we skip this step. So here's the metric. Essentially, think of this acting on a scalar. It is essentially square root of minus G. m, the root of g, n, and then this r. Okay? So it's that. You just apply that operator, and you get something. Now, what you will get is something where you are going to differentiate with respect to z, and you're going to differentiate with respect to x mu and x nu, obviously. So what I want to write, I want to skip a few steps. So I'm going to assume already that my function, phi, so let me write it, is going to be that depends on z and x. X is this 4-dimensional. Okay, remember, this is going to be, I'm going to use some Fourier expansion, and then I have this mode here. Okay, and this is the thing that I'm going to plug into my Laplace equation. So here's the answer after I do all that. So z squared, z squared, acting on these modes, minus, I'm doing arbitrary dimension, but of course, we can focus on d equals 4, which would be ADS 5. Okay, and p squared is the square of the. Good. So now we want to solve that equation. It might not be completely clear, but does anybody recognize this type of equation? Everything's hypergeometric. Yes. So it's some kind of vessel. I mean, these are things that you have seen maybe in slightly different disguise in E and F. But this you can solve, okay? But I don't want to solve it just yet. I just want to give you some. We have a mission, which is to connect with field theory. So that's for that I don't need to solve the whole thing. But here's what I need to see. So it's setting up the differential equation. We certainly have two solutions, and what I'm going to do is to. The solutions I claim are going to be z, some other stuff. There are two solutions as z goes to 0. Okay, so z delta plus, z delta minus, I'm going to tell you what they are. So this I will call normalizable. I will explain in a minute what normalizable means. This one I will call non-normalizable. But roughly, there's a norm with respect to which this diverges. And this is fine, right? That's non-normalizable. Okay, good. So z equals 0. Now we start putting together some things. Z equals 0 roughly is the boundary of ADS. Okay, by definition in GR, the conformal boundary of a manifold is, if you write it like this, is the place where this blows up. Okay, that's z equals 0 is the boundary. So you see that I'm studying the behavior of this field as I go to the boundary. In the boundary is where the field theory is defined. You probably have heard that. So that's already that's what I want to cover. Now these numbers are very easy to get. As I said, I just have to put this expression here and consider the small z limit. In the small z limit, so I'm going to look for a solution. Basically, I tell you how these numbers come about. So you look for a solution of, let's say, z to the alpha. This one actually we can do so that you see that there's no mystery. Everything is just a quadratic equation. So if I take this form and I plug it here in the z equals 0 limit, so here I have two differentiations, right? So I will have an equation like this: z squared alpha minus 1. And then I still have alpha minus 2 because I differentiated 2 twice. Sorry. Then I have this term minus d minus 1. There's one differentiation, so it's alpha z to the alpha minus 1. And then I have this massive term. So you see z alpha sort of factors out, and I get a quadratic equation for alpha. And these are the two solutions of my quadratic equation. And I'm going to write them because they are going to be very important. Delta plus and minus are d over 2 plus minus the square root of d squared over 4. plus m squared. Okay, that's the behavior of my solutions close to infinity. Good. So now let's clarify what this thing means. Yes.
In the action, should we use a covariant derivative?
This is scalar, so I can use partial derivative as well. Good.
Sorry.
Yes.
You say that is the behavior of in the limit when you go to the infinity. What is going to infinity? L?
No. Z is going to 0, but z equals 0 is the
Boundary.
the boundary. I call it infinity, but it's probably
Okay.
it's the boundary. Okay.
What happened to the p squared?
Okay, that part was subleading because it had c squared and there was no derivative, so it was subleading. Okay. In this region, okay. For the full solution, it is important, but now it doesn't matter. Okay, so what I'm trying to do now is okay. So from this analysis alone, I conclude that near the boundary. So let me near the boundary. That would be Chihuahua. The only Mexicans can. So near the boundary, this field is going to have basically more generally. Okay, so this was to get the absolute extreme limit. Now I'm going to start building up the general story. So this will be c to the delta minus, and then there will be another field that I'll call plus, depends on x, c delta plus. And then there are some leading terms. Now, good. So what I want, so let me, okay, there's another calculation at the level of this level of difficulty. No, okay. So you have to do one integration, but to understand whether these modes are normalizable or not, this is normalizable with respect to the action, right? They have finite action, or if the action blows up. So I need to plug just for you to convince yourself that this is correct. What you need to do is to plug this here and try to do the integral. Okay, that's nothing else. And that you will see that for, okay, then you will see that this is normalizable. It's not complicated, but I think that's easy. Okay, because again, it's just plug this and that's it. I mean, one integration to find out whether when z goes to 0, this is finite or infinite. That's it. Okay. So if you grant me that, then now what I'm saying is, or what I would like to say is that these fields carry some important meaning. In field theory, you see the fields live only on x. They depend only on x. They don't depend on, well, they depend on z like this, but they have. And what I want to claim is that this field now, in particular, the non-normalizable field, piece of the field, this piece, defines so this is my claim. The non-normalizable part defines a source for the field theory. So each field, so roughly, this one we did not discuss a lot, but this one we did not discuss a lot, but essentially in ADS CFT, what I will have, so let's say this is the ADS and this is the CFT. So I will have operators, right? Trace f squared, trace f to the fourth, operators in this theory, and they will correspond to both fields on this part, right? And now what I want to convince you is that boundary data of this field, like behavior near infinity, will define either the source or the expectation value of these operators. So that's where I'm going. This is this statement here. So let me give you more argument about that. So if you have an action in field theory, how do you add the source? So let's say you have some action, some zero action. How do you add the source? This is
you multiply it by against it,
like sorry.
Find that if it's J, the current, you multiply it by.
Exactly. So more carefully, we'll do something like this, right? So there's some J, and then this is the operator. And this is how then you go later on to try to compute correlators. Now I want to convince you that this J in field theory is precisely this phi 0. Okay? So now let's do that. And for that I will need some of these numbers. Good. So I can think of, so you can think of just rewriting that over there. Phi 0 of x is the limit. Okay. Okay, so let me. It's really hard to raise anything.
Why don't you use the other ball picture?
That one went there?
Yeah.
Okay. This is a very self-serving comment, so because people from here cannot probably see very well. I'd be democratic. Okay, so what I try to do is that this is at the end of the day what you add to an action. So what is the key thing that you learn in field theory 101 is that this has to be dimensionless, right? The dimension of this operator and the dimension of this operator have to add 2 minus d, okay, or d. So now what I need to do is to convince you, and also, okay, I guess I also mentioned, maybe I did not mention it, but I can also convince you that this z is related to scaling. That was one of the things I mentioned in the SO4,2 story. So let's do that. So let's try to write this. So good. So if this operator has dimension d, then the sort has to have dimension d minus d. So I guess I'm going to write it down. Okay, good. So here's so this is also the limit as c goes to 0 of 5 to x. Into the delta plus and delta minus, they have they have this relationship here, so I can write it as delta plus minus b. So the fact that phi 0 carries, so if you allow me, you have to, in 2 minutes I can convince you that this is related to scaling dimension. Then this combination will have the right scaling dimension to be a source for this operator. So I guess that what I did not, so I had the metric. So let me do it right here quickly. Okay, so the way that I wrote the metric now, and that I will probably write it all the time, was like this. Okay? So in field theory, this part, if I want to consider some rescaling, so let me call it, I guess it's lambda x. You see that this rescaling in field theory, which is the one thing that gives dimension to operators, will give me a lambda. This has to be, as an isometric, it is accompanied by lambda goes to, by z goes to lambda z. So if I do this substitution here, nothing changed. So that's how geometry keeps track of a scaling transformation. But now that tells me that in a field that is scaling with z, it acts as a mass scaling in the field theory. Especially if they add to be the right dimension to pertain to something that I add to an operator. So let's say, let me conclude, or now is the claim. Non-normalizable the non-normalizable, let me call it mode, in the expansion of this bulk field is the field theory source. Okay, so now once we know, okay, so just as a comment, it's not the main claim, I have not completely justified, but if one, okay, there were two modes, phi 0 and phi plus. So if phi 0 is the source, then it's very plausible that phi plus is the what? Sorry? No, it's not the current. So it's the response, it has to be the best. So in field theory, we don't think about it like that, but when we do ADS-CFT, I give you some concrete example of how this works. But these two modes are essentially the key. In linear response, right? So if you have some source, then there will be a response. So that's what ADS-CFT does for you at this level. So you solve for your field, and in some conditions, you can give the source and you will get the response back, if there's a response. So, now, so basically we have worked out if I have a scalar operator, so let me know we can have a table. Actually, we can go to our table here. So if we have a field of mass m squared, it corresponds to some, it will correspond to an operator of dimension delta, which is given by delta minus d. So this is a formula, a very concrete formula that relates for me the mass of a field in ADS to the dimension of the operator in the CFT. And this essentially we saw, okay, I guess that you can rewrite this equation in that form. But I will not do it, but I can do that for many other fields. I can do it now for a vector, for a p-form, for a fermion. For any field in ADS, I can connect via this kind of analysis of asymptotics how its mass connects with the conformal dimension. And here I'm just going to have a list. So for a p-form, is scalar. Scalar, also a scalar operator. So for a p-form, so this would be some determinant operator. So the mass formula would be m squared is delta minus p, delta plus p minus d. And then for spin 1/2 or 3/2, right? Latino under Latino, absolute value of m times L equals delta minus d over d. So, and I can continue this list for whatever field. So that's essentially part of building the ADS-CFT dictionary. Now, for every operator, I have a field in the bulk, and moreover, the asymptotic value of that field determines for me what the operator is doing in the theory.
Is that an absolute value?
Yes.
So could I have something like solitonic, where like with negative mass go to something?
No, in the fermion, the concept of negative and positive mass is a little bit tricky, so I just put a. Okay, so now what we can do is the following. So now this is, we can state the ADS-CFT a little better. So allow me, even though of course I did not completely prove it, but we have some, or we claim to have some one-to-one correspondence between field theory operators and gravity fields. And more precisely, we discussed this. This is the source. Okay. Now, I use gravity fields, and I as I said, I said it in words, but let me write one formula. So the scalar field that I discussed, I ended up discussing in ADS5 because that's where the main dynamic is. But I want to remind you that again, I could have started directly in 10 dimensions, and you see I did this Fourier transform where instead of playing with x, I use momentum. Also, instead of using the angles on S5, I would have used spherical harmonics, and I would just have some number, right? So L plus 4, something like that. So this, when I say gravity fields, in the most rigorous way, I mean that I take type 2B supergravity in 10 dimensions on ADS5 plus S5, and I study a field there. There will be a little bit more technical baggage, but that the essential thing would be the same. Okay, so now we can state roughly what we did. So we have found this ingredient where this is the asymptotic value of the field. So now I'm ready to state ADS-CFT in one of its it's still weak, but one of its cleanest way. So I can now, given if you give me a source, as we already discussed in field theory, I can compute the generating function of, for example, connected grid functions, and this is I compute as exponential CFT. So this is now a prescription, right? This is now a prescription for what to compute. So a field theory object along these lines, I compute by, in this case was simple, but essentially by evaluating. So let me write it. So what we did not completely do it, but what this prescription is telling me is that I need to compute the gravity in this case, in this limit that we're discussing, the supergravity action. So here's the statement of the correspondence at this level. So I want to say that this object I can compute using supergravity. Enhanced by this boundary condition that the limit as it goes to 0, the limit of phi of zx times z to the d minus d is phi 0. So that's my prescription for computing this object, the generating function in the field theory. Okay. So now this answers some of the key questions we had in the morning. How we can use this correspondence. And of course, so once you give me this generating function, I of course I know how to compute correlators. So if I have the correlator of this operator, x1, xn, the CFT, it will be given by differentiating this functional. Okay, so I can compute any correlator in field theory using the supergravity action, the gravity action. So this, okay, so this is sort of one of the main results. As you see, it didn't cost very much. So what I want to do is to now compute some correlators. So that's one of the main calculations in ADS-CFT. It's a very, it's sort of like one of the first that was done. Otherwise, it wasn't clear exactly how to use this correspondence. So let's do that. So, okay. So if I have two operators of dimension delta in a field theory, I'm sure that some of you know the answer. So it's more or less what you know from 2D CFT. 1 over x to the 2 delta. It has to be something like this. Some number x to the 2 delta. So we know what so it's not a surprise, okay? The surprise will be to get this using ADS, only ADS. Okay, so I will show you that. I will show you that, again, sort of schematically, because there are a lot of little calculations, but it's technically it's very simple. So, but that's what we want to reproduce now using ADS here.
Sorry.
Yes. Yes. Okay, good. So that is gravity, right? So the field theory is in flat space. I have not talked about that. Now there is no dilaton. That's probably what. Oh, sorry, there is no graviton. That's probably what you are unhappy.
Field theory is not in the picture yet.
Field theory is in the picture. So I'm trying to compute field theory objects. And I'm telling, this prescription is telling me that to compute this object, I need to evaluate the gravity action, and then maybe differentiate with respect to this boundary value, which is the source, and I will get the field theory answer.
You could get those correlators from the field theory directly.
I could if I could in some cases, but in many other cases I cannot. Okay, so if I am talking about a strongly coupled field theory, right, I certainly cannot do it.
What is the conjecture? Because it seems to me like you already made a correspondence between which part that cannot be proved that makes it ADS-CFT correspondence conjecture.
Okay, so I have thought a lot. I continue to think about dualities and what is provable and not provable, etc. So for me, provable would be you give me some object defined by its path integral, I manipulate that path integral, and I get to some other object. That for me is proof that theory A equals theory B. Short of that, is not a proof.
But what might you prove in order to say that theories are equivalent. That all the correlators are equal.
Right, so in principle, in a conformal theory, I need, it's a little bit trickier. So the 2-point correlator are still determined by the spectrum of the theory, roughly. You think of deltas on energy of the operator, and that's it. 3-point is also more or less determined by conformance. 4-point and above are not. So if you can compute all correlations in a field theory, then yes, you'll be done. But that's usually not possible. Good. So don't hesitate to ask whatever kind of question you have. Okay, so but I have a prescription, and I'm going to use it. I have already written the equation for a scalar field, so I'm going to go back to the scalar field. So here I'm going to go back to a scalar field, and I already wrote the Laplace equation, so now I'm just going to write the answer that I mentioned. So, okay, now let's be schematic. So I have dc dx. Again, so again, think of this piece as something that came from an honest type 2B in ADS5 plus S5. So here I already have the so let's evaluate this action, because this is what my prescription tells me, that I need to evaluate this action. Okay, so let's do that. So this action for fields that satisfy the equation of motion, the on-shell action, is actually almost zero, right? Because fields that satisfy the equation of motion are going to be almost zero, except for a boundary term, right? So just think of this derivative, right? So I have d phi. I want to write it. Usually, what we do is we write this as this. Well, not this operator. So. Right? And then there's a boundary term. So because this is the on-shell action, this part will not contribute. So the whole thing that I need for my ADS CFT will come from the boundary. So let me write it. It will be minus c over 2 in the normalization I wrote before. X over g dcc phi zx dc x. This is at z. Okay, now subtleties are starting to come in. Okay, if I put, so let me just write this expression. So square root of g times g cz is essentially L to the d minus 1 over z. So if I put at z equals 0, I will get a divergence. Okay, that is good, because we expect that if you are dealing honestly with the field theory, we should have some divergences. Now, there are fancy ways to deal with these divergences. They are called holographic renormalization. When you will do what you do in field theory, you add all possible counter terms, and then you can cancel different divergences using counter term, and then you have to use these counter terms at the next level. So that machinery exists, but I'm going to use something a lot simpler, which is some sort of subtraction, which is called. Okay, but again, just be aware. Okay, so now what I'm going to do, I just have to put the solutions of the equation of motion here. So let me write the solutions. So I'm using this z and p, because I did Fourier transform. So there will be some function here, c z over 2. This would be Bessel, c absolute value of p. This is, of course, the square root of p squared. And then I have another mode, z over 2. This is I. So this is what I said before, that the solutions to the equations are Bessel function. Now, this one blows up as z goes to infinity, which is in the interior of ADS. So I will make dp equals 0. So here's my solution. And what I said here that I have to deal carefully with this piece means that what I'm going to actually do is I'm going to normalize it the following way so that I don't deal with some of these divergences. So clearly this AP is going to be related to what? Source, right? So I use phi 0 somewhere, but it's essentially this piece. And so the phi that I'm going to write is d over 2, k mu, 0 over 3. So this one I will normalize this way. This epsilon is where I put the boundary now. Okay, so I know it's a little bit long, but it's not too bad. Then I'm just now going to write e to the d minus delta. Okay, so that's my field, and now what I need to do is to evaluate this. Okay, so there are two technical aspects that I need. But again, I will not do it. It's done in many papers. The first person to do it was Gubsev, Klebanov, Polyakov, and then Whedon. So this is the paper that somehow, well, not somehow, but the paper that gave some framework to Maldacena conjecture. So Maldacena wrote his conjecture, and then this paper told us this is how you compute correlators. So it's an important part. But anyway, so you know technically what you need to do. I need to get to correlators, I need to find the action and differentiate the action with respect to the source. That's all I need to do. Unfortunately, or as you wish, to evaluate the action, I have to evaluate this boundary term. It has a divergence, so I regularize. That requires that I normalize my solution, which I have done. And now I just have to plug in here, differentiate, which I believe you absolutely can. And now I have to take this limit of epsilon goes to 0. So, but to get the limit, okay. So let me tell you what are the things that. So we're almost done. So you will need some k mu identities. Okay. So I have them written, but I don't think we will write them now. And then differentiate. So then I'll just differentiate S with respect to sources. So there's no other stumbling block in this calculation. So let me. Okay, there's one subtlety, but. Is this being recorded? Okay. Then I'll do it in private. No, because there's a subtlety. I want to mention it. Okay, I will not say who overlooked this subtlety, but you see, once you put this cutoff here, okay, you no longer have the full ADS. So you no longer have the power of all group theory that we use. Because with group theory, this problem could be a lot simpler. It's a symmetric space. It's like finding distances in the sphere. So in principle, it's complicated, but you know on the sphere, you know the geodesics, and you can just construct them. So in ADS, you could in principle do the same story. And then you can solve this problem very quickly because it's a matter of finding just some distance between points and differentiating. But that you cannot do because you have destroyed the space, okay? So that's the subtlety that some people have overlooked. But okay, so this is the question. So now what we want to evaluate, let's say OP, OQ, this correlator, the momentum space, but with this parameterization, this we say is 2 pi. Sometimes I write the numbers because I have them here, but not essential. Okay, this is now the differentiation I need to do. This is my S that depends on phi 0. Here, I differentiate twice, and I take the appropriate limit. And what I'm going to get is so let me define D is delta T. So I can talk about this in a minute. There's some constants. I'll have T to the T mu, and then I still have some log of X. There are other things that doesn't matter. But this is the answer. Okay? This is the answer for the correlator in momentum space. I can remind you, if you want, of one more identity, which is how to do Fourier transform of that into the ITX. T to the n goes to some many numbers, x. Okay, so now you apply this identity, this Fourier identity, to this answer, and you will get exactly what is there. Nu, of course, I didn't tell you what nu is, but you can figure it out. Nu is, let me just be completely sure, but nu has to be this part of dA squared over 4 plus m squared. So that everything works out. Okay, I know it might not look very impressive, but it should be impressive, right? So you are doing some calculation of a scalar field in ADS, and that, with the appropriate prescription, gives you an answer corresponding to conformal field theory in one dimension lower. Good. So let me put it in this blackboard. So we have learned two things from phi. C x as C goes to infinity, sorry, to the boundary, we get the source. And then using the source, differentiating the supergravity action with respect to the source, we get correlators. Now, good. Any question? So this is essentially the end to the introductory aspects of ADS-CFT. So now you know what the thing states and how it works in these simple cases. So from now on, I'm going to start doing things that are interesting, but they are not, at least not essential to the formulation and the statement of the correspondence. Yes. So now, yes.
Really taking the fact that you're working with a medium scale. You mentioned initially that.
Good questions. Thank you very much. So there is an abelian field in the background of all this, but I have not used it. I'm using a scalar because operators that are scalar are the nicest, so that's what I'm using. Now, this is a very important object. It's a very important statement of ADS-CFT. So this all has to be gauge invariant operator. Okay. So the gauge invariance is enforced in the sense that the bulk fields in gravity, are due to gauge invariant combinations of fields. So in fact, this will not be dual to the gauge field A in gravity, in field theory. So there is no object, right? There is no, because that's not gauge invariant. So there is no object in the bulk that will connect to the gauge field in the field theory. It will connect to gauge invariant operators, gauge invariant combination operators. That's a very crucial question.
How about gauge covariance?
Like,
Like the curvature?
so the curvature is gauge, I mean, I have to form a gauge invariant. So I have to form trace f squared. So f, I will not get it.
So I could apply all these in the big form. I started with an also big form in ADS.
Okay, but
What's the difficulty?
yeah, there's no difficulty. So you will discover this. But you need to understand what operator will have this kind of symmetries. Okay, that's it. And most likely will be some antisymmetric combination, gauge invariant antisymmetric combination of many derivative acting on some operators. Okay, good. So now I want to do this is important. So let me write it. So now I'm going to do the Wilson loop. The simplest Wilson loop. There are many Wilson loops, and this is sort of my favorite subject. So, so I'll talk about Wilson loops a lot. I promise also to talk about finite temperature. So tomorrow I probably do finite temperature, and then I close with Wilson loop. But today I want to start with the simplest Wilson loop. Yes?
How crucial is it that this is a CFT on the boundary? Could it be some, because in a CFT you know that
Yes.
SOP has this expression which you
Yes.
mentioned it. You don't need more information about the operator. But could it also happen in a non-conformal field?
It can also happen in a non-conformal. Now, it can happen, but I do not have power to tell you that it has to happen, right? So, and this is really a very crucial moment. So this is really a very crucial moment. So there's a framework in N equal 4 where we have solid arguments that this is indeed the case. Now then what most people do is to take the lesson and run it and hope that it is true in other cases. There's of course a lot of work. All the work that was trying to connect to QCD, of course QCD is not a conformal theory. In QCD you will not compute this correlator, you have to compute something else. But the prescription is here. You always have to end up evaluating the gravity action. So the Wilson loop, I want to give it as an example because it is the first example in which it's not the gravity action that you want to evaluate. It is in fact the stream action. Okay? So I wanted to make, I want to write something. So let's try. So today in the morning I spent a lot of time saying I want a effective field theory of these very low level modes. All alpha prime modes are over here, and I want them to decouple. Okay? But then if you follow my argument carefully, when I was talking about the part of modes that live very close in ADS, they can have very high energy, arbitrarily high energy. Still, they look very light from the boundary because of the redshift factor, but they can be very large. So in principle, there are many elements in ADS CFT in which I will be able to get to some of these higher dimensional operators, or if you wish, a higher mass fields. Okay, because so I want to talk, as I said, I want to talk about the Wilson loop. So I don't know if I should first do the calculation and then the sermon, or vice versa. But this is really important because this is not a gravity mode. You see, this is not a scalar field living in ADS. This is a very heavy object, right? It's a string. And I still going to claim that it is part of ADS CFT, and it will give me information about some other objects. So that's why it's a special example, and it will of course correspond. A Wilson loop doesn't have a conformal dimension. It's an operator that is not classified like that, but it's very heavy in some sense that we will see. So let's do that now. So I need some prescription. Okay, so how many people know what the Wilson loop is? Maybe I'm also running ahead of myself. Sorry, the question is always the wrong. So how many people don't know about the Wilson loop? Good. Okay. So let's. Okay. Good. So let's start with some very introductory statement about the Wilson loop. So in QED, and I guess that Clifford also mentioned, you can construct. You can call it holonomy. You can call it. So if you have some curve, C, in a space, you can move a charged particle around it, and just measure. So usually we charge here. So that one you can of course do, and that the key thing is what is the physical information that this object gives you. Okay. So certainly we can do this in more complicated theories. We can do it in gauge theories as well. So non-abelian gauge theories. I'm sorry. So there I need to take the trace. I need to path order. And then again, I just take a mu, but now of course this contains all the generators. So this is the Wilson loop. Now what is this object good for? Okay, so what is this good for? So it has many important uses. So one very important use is that it is another parameter for confinement. Confinement. Okay, does anybody remember what is the story with confinement and Wilson loops? Okay, so the story is that if you evaluate this object and it is proportional to the area enclosed, then you are in a confinement theory. If it is proportional to something else, then you're not. You're not in a confinement theory. So that's, yes?
Trace of what? P what?
Okay, trace, path order, exponential
Okay.
of this thing. So let me try to argue. So suppose that we are in Euclidean context. So we're going to take a rectangle, as the Wilson loop is going to be a rectangle like that. So this is T, and let me call this D. Okay. Now, because so I didn't write it, but you assume that you have some. So you see the charge and the orientation of the contour are more or less correlated, right? So if I go like this or around, so let's do this. If I go around, I can think of really taking my charge. In this case, let's say I take a quark and I move it around my theory like this. But I can also think of this as a quark and an anti-quark that I created here. Then they sort of propagate in my theory, and then they disappear. So this is telling you this can connect. Okay, so this analysis or this intuition should connect with confinement. So if I can, if the probability of having quark anti-quark being created and go for some length of t and then annihilate. So this object should convince you that something is going on along those lines. And more importantly, also for people who work in lattice QCD, so if you take the limit as t goes to infinity of the expectation value of the Wilson loop, this I hope that you have done in quantum mechanics. If you look at something like this, if you're looking at a transition like this, there's only the lowest lying state survive. So there's a similar philosophy here, and if this is this, we can use as T. So where this is the potential between quark and anti-quark. Okay, so that's why this object. Those are some of the reasons why this object is very useful. Now I have to give you a prescription. Okay, so this is sort of the end, introduction to Wilson loop. So one last comment is that for the more advanced students, is I'm just going to write something like this, loop equation. And this is an attempt by Polyakov and others to try to reformulate field theory, non-abelian field theory in terms of the Wilson loop. So the Wilson loop is such a powerful operator, it generates all other, it's a non-local operator, right? It depends not on a point, it depends on a contour. And it is so powerful that you can expand, and it contains in itself all operators of the theory. So you can try to redefine your theory in terms of this operator. So that goes by the name of the loop equation. So it's a very powerful operator, and we would like to see if ADS-CFT says something about it. Of course, the answer is yes. Otherwise, I wouldn't be telling you this story. So let's see what happens. You see, this is a diagram that I drew in field theory. So now I can do like this. Okay? And then my z is in this direction, let's say. So this is z equals 0. So this is how ADS is now going to live. So there must be some object in string theory that will sort of satisfy this boundary condition. So these are field theory. So they must be met by some object. Okay? And then, okay, you start shopping around, and there's only one object that fits this shoe, and it's a string. So, because a string can end in precisely this contour, but then it will extend, then it will extend into the bulk, and basically give me a surface like this. And evaluating the surface of this string will be like evaluating the gravity action before. So that would be the generating function of the object I'm looking for. Okay? So again, it's not something I can completely prove, but it's very plausible, and then we will see. So is this idea clear?
What is that string?
Okay. So the string is a wall sheet, right? So it's this thing that enters into ADS.
Okay.
Okay.
It will be working in ADS.
So yes, I assume that this field theory, everything that I said in field theory was in this R1,3, but then because if this has some dual, it will has one dimension more. This sometimes is called holographic direction, and it goes into the bulk. And now what I need to find is an object that has these boundary conditions to be a Wilson loop, but then of course it goes into the bulk. Okay, so this actually would be a point in the calculation. So there would be I can think of this surface as something that has a turning point, and I can determine where this turning point is. That's what you're asking, whether this is close or deep. So this usually depends on the geometry. We will see that here it doesn't matter much, but in confining backgrounds, and this is essentially how ADS-CFT works. So you do something for ADS5 plus S5, and n equals 4 that you know works, and it gives you a sensible answer, and then you say, okay, this prescription I take it somewhere else. Let's see what happens. So I can do this I'm doing it in ADS5 plus S5, and I know that this is dual to a theory that is not confining. So I cannot get area law here, right? Because it's not a confining theory. But I will get something that makes sense, and then I believe, and of course, if I do it in something, then I can take it to backgrounds that I believe are dual to field theories that are confining, and it gives me something that makes sense. Okay, so now I said I want to consider a string, and essentially, as you can see, I have some surface, so the natural thing is to find that surface. And how should I find that surface? Sorry? How? Minimizing non-Bugotto. So this is a string. The action for a string is non-Bugotto. Now it's non-Bugotto in this space, but I know how to get minimal face areas or minimal Euler-Lagrange for anything, right? So that's what you spend the first year of physics doing, just classical mechanics and things like that. So this problem turns into a classical mechanical problem. Let's do that, and then I'll write the answer. So what happened is that, okay, so I have the metric. So let me write directly the induced metric. This is easy to check. Okay, so L squared over C squared. Okay, so let me, so this direction one, I'm going to call it X1. Now this one I already called T, sorry. But it's Euclidean, okay? But this one I would call X. X1, one of this direction. So let me, this is a little bit too crowded. So maybe let me take, so this is the X1 direction. So this is 0. And this is where the string, so this is another screenshot of this string. So the string is going to do like this, right? And then this is C equals 0, and this is, let me call it C star. So you know the metric of ADS. All I'm saying is that all I'm going to say is that this Z will now depend on X. That will give me this profile. So the whole thing is that Z will depend on X. So when I plug that in here, I will get that my induced metric is dt squared plus dx squared that multiplies 1 plus Z prime squared. And now I want to construct the action that I have to minimize, 1 over 2 pi alpha prime dt dx square root of this T induced. And this is essentially T L squared 2 pi alpha prime dx square root of 1 plus Z prime squared divided by C squared. Okay, now, as I said, now I'm back to some maybe advanced high school problem. So this is a Lagrangian. I can think of X and T, right, as my time, but it's just classical mechanics. So is this clear? This is step clear. So this is the induced metric on this worksheet, right? All other X2, X3 are constant. Right? So they don't enter here. There's no pullback if you allow me. Okay, and then the determinant of this one is precisely this expression. So the determinant will be the product, right? So square root is this, and then C square square root is this. So, and now I have a classical mechanical problem. No mystery. I can solve this problem. Of course, I can solve it using Euler-Lagrange. And I already have my Lagrangian here, so it's but there's even something simpler, and the fact that, you know, if this is a classical mechanical system, and X is my time with this system, then this is independent. It does not depend explicitly on time, so there's a conserved quantity. We call energy in this case, but it would be the X energy. But there's a conserved quantity that I can use. Good. So I guess that's it. So let's talk about also boundary conditions. So I want, what are the boundary conditions? So the screen returns at this point. This is d over 2. Or yes, and this is minus d over 2. So z minus d over 2 equals z at d over 2 equals 0. Okay, and then this problem is solved even simpler if I just consider this piece, this part, where z goes from z star to 0. And
what's Z prime again?
Z prime is here. Here is the z dx. Because I'm embedding this. So the constant of integration, basically this constant of motion here, will of course be related to this constant. So the more energy you give it in X, the more it can go deeper in this direction, roughly. Okay, so it's not. So let me write the equation. So the solution will be like this from solving Euler-Lagrange. C star to the 4, C to the 4, over C squared. I can use this to compute. I can now use my boundary conditions to connect this with D. So which I will do. So again, I can rewrite this as dx. So this z over dx, and then I integrate over z, and I integrate over dx. And let me square off those details, but essentially what I have is c squared integral from yeah, 0 to 1, y squared dy square root of 1 minus y squared. So y was, of course, I rescaled this z star, it appears here. So this is part of it. So remember that I'm looking for, I would like this to give me something from which I can read the energy between a quark and an anti-quark in this theory. Okay? So I want to evaluate this guy. But it would naturally will evaluate as a function of C star, and then I will substitute C star by D. So this is some number that I will not bug you with, but some gamma function, doesn't matter. Okay, so now we are done. We have solved the equation with the right boundary condition, so it connects this Z star with the distance that I want. Now I need to evaluate this. Okay. So the evaluation of the action is going to be, again, simple. So twice, because again, I'm going to evaluate this half, but then this is symmetric, so twice. Then I have T L squared, C star squared, divided by 2 pi alpha prime. Integral from epsilon, again, you see, I really cannot, whenever I want to touch z equals 0, I will have divergences because of the same argument. So I will have to C star of z over c squared c star to the 4 minus c. Okay, I don't, okay, so that's the answer. It's Joseph, but we still have to massage it. Now there's one piece of physics, which is divergence again. So in the case, so these are UV, well, okay, so in the field theory, this would be UV divergences. In the case, in the previous case, I really used some cheap trick. I told you, okay, I'm going to normalize my field, and then I carried it around until it was no longer needed. So here I'm also going to use some cheap trick, but it's a little bit nicer because it's physical, okay, it's a little bit more physical. But, okay, but again, bear in mind that divergences are not, are really like in field theory. So you have to understand what it comes from, what it means, and how to deal with it. As I said, there is a machinery in ADS-CFT to deal with them systematically using gravity counter terms. Okay, it's called holographic renormalization. But it in itself, it will take a long time to develop. Okay, so now this is an integral. Again, there's a piece that is divergent. I don't want to bug you with a lot of details. But essentially, I'm going to evaluate this and immediately divide by t to get the energy. So what I get is the following. The energy of quark anti-quark is minus 4 pi squared L squared. So there's some numerical factors here. 4 alpha prime. Now the key thing is 1 over t. So 1 over d, should we expect this, yes or no?
What?
So the energy between a quark and an anti-quark in this theory go with some number 1 over t, the distance.
No, because combining potential goes like this area.
Right. So if we were confining, we will have d in the numerator. right? But n equal 4 is not confining. It's conformal. It's like Coulomb. It's fine. And that's what we see. So this makes sense. Okay? If we do the same calculation in some confining background, some confining geometry, that is not ADS, we should expect D here. And indeed that happens. Okay? But this makes sense. Now what I wanted to mention is that there is another piece, L squared pi alpha prime, 1 over epsilon. That is the divergent piece. Okay? Now, in this particular calculation, with 2 more minutes of algebra, I can convince you that this corresponds to the masses of these quarks, some static mass, and that of course is not, I should not count it as a quantum-quark energy. So therefore, I really consider this as a constant piece that I will renormalize because it's just the mass of a very heavy quark. Okay? But again, be aware that these things appear consistently and that you need to find a way to deal with that. So this is, let me write this answer now using, this is still mixed gravity language. So let me rewrite it in field theory. So the V QQ for antiquark potential is going to be minus 4 pi squared, square root of lambda, divided by gamma quarter 4. So that's the answer that we get using ADS-CFT. Okay? So this is something very difficult. You see, this is something very difficult to get from n equal 4 perturbation theory. In fact, the answer from the n equal 4 perturbation theory is the following. So in n equal 4 to first order in lambda, this would be minus pi lambda over d. So, okay, 1 over d, we can understand generically, but you see, it is complete. This, let me call this weak coupling. Right, this is small lambda. So, and this is the string theory. String theory now gives me large lambda result. So it gives me completely new information about, obviously you can say, okay, this was such a simple system, completely conformal, nothing happens, it has to scale like this, but this is not trivial. And this is what happens, okay? So when you go to strong coupling, you don't know how to do the calculation using Feynman diagrams, etc., but you can use ADS-CFT, and this would be the coefficient. This is square root of lambda appears. It's very different. It's not even, okay, it's very different from, this would polynomially be polynomially corrected, but that's not what's happening in this case. So that's okay. So that's really a computation I wanted to show because it is ADS-CFT, but it is not really gravity mode. So gravity mode was what I showed you before, objects that I take from supergravity, be it the scalar field or some forms, and they come to some operators. But ADS-CFT also has access to objects that are very heavy in some sense, in the sense that this is very large. It's not, if you think of the expectation value of this, I can construct something even nicer, but the idea that I'm going to objects that go like this is really, it's really an advantage. So I guess that's what I wanted to tell you today. Good. I don't know. Nobody knows, but there I will tell you on Thursday cases where I know that this is the right result because I can compute it in using all the techniques. So there are some situations in which you have supersymmetry, and there I can compute quark potential exactly. Okay, and that I can try to reproduce from the string, and it matters. Okay, so you have to believe that interactions are completely decoupled. So yeah, so I mean there are many loopholes if you press them. But, I mean, yeah, many people are completely happy with this story. I'm just saying that it has limitations. So like when we want to apply it to something non-conformal, then we don't have the whole machinery of deep brains and looking here and looking there. So then we just make assumptions like, okay, if this works in this limit, then probably I can extend it and it will give me something sensible in the other limit, but it's not proof.
A conformal field theory is not a combining theory.
Yes.
So, as I know, when you introduce a black hole, for example, you
Yes.
have a thermal ADS, and so you can have a phase transition
Yes.
of terms of another. But in that case, the theory in the boundary is not conformal.
Okay.
So ADS CFT does not require a conformal theory, or
Okay, so let me repeat it again. So most of the arguments that were completely solid, fairly solid, that we discussed today, they connect a conformal theory with a gravity theory. Okay. Now, in a theory, I mean, if this is the power of this, and I hope that you have seen it today. So I can, when I have a theory, which means I have all list of all possible operators, then I can start deforming the theory. I can add a source to that theory, and I can give a vec to some operators in the theory. I can do things. So ADS-CFT allows me to do that. Okay. Around conformal theories, that was this calculation. I put a source, and I can see how the theory reacts to the source by differentiating, and I can compute correlators. That I did. That is still mild deformations of the conformal theory. So now, then there are truly non-conformal theories. Okay? And so the gauge-gravity correspondence seems to work very nicely in many cases like that, but it works without the justification that we had in the conformal case. Finite temperature is a slightly different story, right? You can also put a conformal theory of finite temperature. Yes, it's no longer exactly conformal, but it remembers where it came from, and many things are not that dramatically different. The phase transition is a different story, so that has to do with it. That's slightly more complicated, so I'd rather not go into that right now.
if there is no question, please take the